Today I'm going to talk to you about PV diagrams, which are diagrams which help represent a process in thermal physics in a closed system. And it all starts with the relationship of the ideal gas law, which is PV equals nRT. And this relates pressure and volume to the number of molecules, a constant, and the temperature as measured in Kelvin. The basic setup for a PV diagram is to have two axes. The y-axis is pressure, and we'll have that in pascals, which is a Newton per meter squared, and volume as your x-axis, and that can be in liters. And then what I'm drawing now are isotherms, and these are contour lines that represent the same temperature. Every point on each isotherm has the same temperature, and this is because as pressure goes up and volume goes down from the ideal gas law, the temperature stays the same in the system because the number of molecules doesn't change in a closed system and the constant only affects the magnitude. So as pressure goes up and volume goes down, they kind of counterbalance each other when they're multiplying and they have the same temperature. But when both of them go up, from like this isotherm to that isotherm, both pressure and volume have gone up, then it has a higher temperature. So each one of these has higher temperatures as it goes away from the origin. One of the processes that I'm going to talk to you about today is called isobaric, and that is when the pressure remains constant. And you can remember that because pressure is measured in bars, so it's isobaric. And to represent this on the diagram, you can draw your first point, which can just be 1 Pascal and then just 1 liter. And when it changes, it's going to keep the same pressure in a straight line and expand in volume to say 3 liters. And we use a point to indicate the start and then arrows to indicate changes. And then it's also helpful to label what step in the process each point is. The most common question is when they ask you to draw out the process, but they'll also ask you how much work, for instance, was done in this process. And that is represented by the area under this curve here. And you can see that through dimensional analysis of when you're crossing these, you're multiplying them, pressure times volume, that's the area. And pressure is newtons per meter squared times volume, which is meters cubed, and then you have Newton times meters, and that is work. I changed the pascals here to kilopascals to make the math easier. So here it's 2 liters, and a liter is 1/1000th of a meter. So 2/1000ths of a meter cubed times 1,000 pascals equals 2 Newton meters, and that's also a joule. So there were 2 joules of work done in this process, and you can see this to represent this visually. It started out as 1 liter of gas here, and then it expanded to 3 liters, keeping the same pressure. So actually the work was kind of negative if you want to think about it like that, because the gas is actually working the piston. So in the internal energy equals work plus the change in heat equation. If the work is negative, as in this case, then we can know that the heat was positive. So to keep the pressure constant in isobaric cases like this, heat has to be added to the system. Another process I'm going to talk about is isochoric, and that's where the volume stays constant while the pressure changes. So we would start here and keep the same volume of 2 liters and decrease from 1 kilopascal to half a kilopascal. In this example, there's no work because there's no area under the curve. And to see this visually, the piston is just remaining where it was and not working on the gas, and the pressure is just changing. So that's why there's no work. In the equation of the internal energy equals work plus the change in heat, since there's no work in the isochoric case, and the internal energy got lower in our example, since it decreased in isotherms, that means that the heat must have decreased, so it escaped from the system to make the pressure lower.